Alright, welcome back to Clear Creek Solutions instructional videos. It's more hydrology education. We're moving on to the hydrologic cycle. That's what we're going to cover in this video. If you want to learn more about hydrology, the kinds of hydrology, water resources engineering, how we calculate flows and design, you can download the Ultimate Hydrology Guide down below. It's 100% free to learn more about the different forms of hydrology. Quickly on Clear Creek Solutions, it was founded in 2005 by Joe Brasher and Doug Bayerlein. We do software development, hydrology solutions, and modeling, as well as developing the wwhm 2012 software package for Western Washington. Let's get into the hydrologic cycle. So first off, the world's supply of fresh water is quite small when compared to the saltwater supply globally. So if you think about the freshwater sources such as rivers, a lot of lakes, streams that come from freshwater rain, and you compare that to the size of the oceans and saltwater lakes and bodies of water like that, it's quite small. There's a lot less fresh water on the earth than salt water, and as we know, of course, fresh water can be consumed, but salt water cannot be consumed by especially humankind. Freshwater supply is renewed through the hydrologic cycle, which is what we're going to get into. Water evaporated from the oceans is then transported over the continents by moving air masses, and that's where we're able to get some of our precipitation and rainfall. Cooling occurs when the moist air is lifted to higher elevations. So the higher that air is lifted and that moisture is lifted, it's just going to get colder and colder. Since air pressure decreases with elevation, the air expands as it is lifted and cooled in accordance with the ideal gas law. So the ideal gas law is the governing equation when it comes to this aspect. So we've got PV divided by T, pressure. So for the ideal gas law, we have pressure and volume divided by temperature equals the ideal gas constant. The lifting can occur in multiple ways. There's orographic, frontal, and connective. Orographic lifting occurs when the air is forced up over the underlying terrain. The frontal lifting occurs when the air mass is pushed up by a cooler air mass. The boundary between the two air masses is called a frontal surface. And then finally, the moist air must be heated from below as it passes over a warmer surface, causing connective lifting, which may result in a convective thunderstorm. Often two or more of these mechanisms may actually take place together. So roughly 2/3 of the precipitation that reaches the land surface is returned to the atmosphere through a variety of methods. Evaporation occurs through surfaces such as plants and vegetation through plant transpiration. So the remaining third of the precipitation returns ultimately to the ocean through surface or underground channels. The large percentage of precipitation that has evaporated has often led to the belief that increasing this evaporation by construction of reservoirs or planting of trees will increase the moisture available in the atmosphere for potential precipitation. So, and then only less than 10% of the moisture that passes through the Earth's surface is precipitated. So down here I have a much more simple diagram here showing the hydrologic cycle. I've shown this before. We have precipitation. Some of that intercepts into plants. It will become interflow, sometimes groundwater going back into these bodies of water here. Then it will evaporate back into the atmosphere and through evapotranspiration and then rain again. And then it can become surface runoff going back to the bodies of water and so on. And the cycle repeats. So the water cycle is actually much more complicated for any one diagram to show. So there's a lot going on in this diagram, in this aspect. And it can't all be summed up in just through one simple diagram here. So the science of hydrology is devoted to studying the rate of exchange of water between phases of this cycle. And what we do is the information is used for hydraulic design. So rainfall information is incredibly important when it comes to hydrology and design of our facilities. There's many formulas that are then derived from this precipitation and used for design. So in a software package such as wwhm 2012, we use this rainfall and precipitation data to determine what kind of runoff we're going to get based on the land use area of our project site. If we have forest, it's going to have different runoff than if we have impervious surfaces such as roads. So the amount of precipitation, how that precipitation acts, and getting as much as that historical rainfall data is very important for hydrologists and for designing our facilities. So the river basin or catchment is the area tributary to a given point on a stream. So and is separated from adjacent basins by a divide or ridge that can be traced on topographic maps. All surface water coming from this area is discharged at the lowest point, since water tends to trend toward the lowest point. And then groundwater movement conforms to the surface divides, and it is commonly assumed that the movement of groundwater will conform to that surface divide, but this assumption is not always correct, and large quantities of water may be transferred from one catchment to another as groundwater. So that's our overview of the hydrologic cycle. You can see some of our other videos here in this Learning Hydrology series, and we'll see you guys in the next video.